Hey everyone, we'll go ahead and get started now. And so today we're going to be talking about classification and also about training neural networks, and that's kind of much more general than classification. So we'll talk about a lot of principles today for how you actually implement training of neural nets that's going to kind of generalize well to other applications in the class. Okay. And so if you remember last time we talked about different CNN architectures, these CNN architectures underlie image classification. And so today we're going to learn more about how to actually implement classification in practice with a heavy emphasis on how to train neural networks. And as I said, this discussion of training applies to many different types of neural networks, not just those that happen to have a classification head as the final layer of the network. Okay, and so if you remember from the lecture where we introduced different concepts in deep learning, we talked about how we can think about neural networks as Legos, where you stack together different layers or different types of Legos to make kind of different network structures. And classification is probably the most straightforward thing you can do. So in the context of image classification, you just stack a classifier layer on top of the CNN features extractor like ResNet or VGG that we saw last lecture. We already saw this when we looked at some of the CNN architectures last time, where the final layer after the features network output ImageNet class probabilities. And so remember in ImageNet there were around 1,000 classes, and the final layer took those probabilities down to like 1,000 class probabilities. Okay, and so in the context of classification, generally there's two loss functions that we would want to optimize, and they're used they're similar and they can be used interchangeably. And so if you remember, we optimize the network by minimizing the loss, where the loss takes the difference between our output from the forward pass and the ground truth. And so the first type of loss function for classification is called SVM loss, for support vector machine loss. And so what SVM loss does is to sum over the incorrect classes, taking the difference between the scores of the incorrect class and the scores of the correct class, and you want the correct class to have the highest score with some kind of safety threshold, which we'll set to 1. And so just to give an example of how you would calculate this loss function in practice, so suppose that we have data with just 3 classes, class 1, 2, and 3. Class 1 has a score of 3. In the final layer, class 2 has a score of -7, and class 3 has a score of 2.5. And the first class is the correct class. And so if we wanted to compute the SVM loss, that's first of all, the max of 0, or the comparison of the second class to the first one, which is correct. So just -7 minus 3 plus 1. And so that is equal to 0. And then we have to compare the third class to the first class, which is the correct one. So that's just a max of 0 and 2.5 minus 3 plus 1, which is actually a positive number, because it is true that the first class has a higher probability than the third class, but only by a modest amount. So it doesn't get us over that threshold to have 0 loss. The second class, on the other hand, the score is much lower than the true score. So that's going to be a loss of 0. Of course, you'll note, that score could have been 2 instead of -7, so much closer, and that would still be a loss of 0, as long as the difference between it was above that sort of threshold of 1. And so in other words, with SVM, the loss doesn't care, how, about the magnitudes of the scores per se, as long as the difference between the class score and the true class score is above the threshold. And so, Another thing you might note here is, why did we choose a threshold of 1? Like, isn't that a hyperparameter that we would have to optimize? Actually, you can show that we can just set that threshold equal to 1 without loss of generality. And sort of the intuition there is that you could set it to some other number, but then the weights could just scale things up so the differences were larger or smaller. And so we can just set that equal to 1. And what we're looking for is, let's compare each class score to the true class score, see that difference and whether it is greater than some threshold. And so in practice, you'll see SVM called a hinge loss, and that's because the loss function looks like this, right? It's kind of increasing linearly, and then it goes down to 0, and it stays at 0, no matter how much you crank the correct class score above the other scores. Okay. So the second loss function that people use for image classification, and also for a lot of other tasks, we'll see this a lot with NLP as well, is Softmax. And so essentially, the Softmax function takes a vector of any arbitrary real valued scores, like the one that we saw in the last example, and it squashes that vector to values between 0 and 1 that sum up to 1. And so, like, loosely speaking, you'll see people interpret this as the normalized probability assigned to the correct label, given an image xi, and assigned to each of those incorrect labels. It's worth noting that how peaked these probabilities are depend on your regularization term, which is something we're going to talk about later in this lecture. Regularization is a term you add to your loss to avoid overfitting. And so, technically speaking, you can't really interpret these as probabilities. If the true class has a score of 0.95, it's not that you're 95% confident that it's correct, but you can interpret the magnitudes of these. And so this loss, which is also called the cross entropy loss, then minimizes the cross entropy between estimated class probabilities and the true distribution, where the true distribution has all the probability mass on one class, right? Because we know what the true category is. And so alternatively, you can just interpret this loss as minimizing the negative log likelihood of the correct class, which you can see from the form of the loss there. So let's say that the probability on the true class is 0.7. Then the loss is just the negative natural log of 0.7, which is 0.357. If we're not doing so great and the probability on the true class is only 0.3, then the loss is the negative log of 0.3, which is 1.2. If we're doing really great and we push that probability all the way up to 1, then the loss is 0. Of course, in practice, you're never going to get precisely a loss of 0, unlike with the hinge loss, where you actually kind of could in theory. And so both SVM and Softmax are frequently used for classification, like, the ImageNet classification we saw, but as I said, we'll also see classifiers as, kind of super important in natural language processing later in the class. And so to think about how these differ, with SVM, once you get the right answer, above the threshold of 1, it doesn't care if you push the score for the correct class even higher. Whereas in contrast, Softmax cares about pushing the probability of the correct class all the way to 1, right? Because your loss is just the negative log of the probability of the correct class. And so what this means in practice is, if you're training a network with a Softmax classifier, you might see early on in training, your loss is barely changing, but your accuracy just jumps up, right? And that's because you're kind of, getting over the threshold to get things correct, but your loss is changing continuously. And so if you see that, it doesn't mean that something's wrong. You can actually have kind of your accuracy jump, but your loss just change smoothly with Softmax. SVM is like more of a local objective. And, some people argue this is a bug. Some people argue it's a feature. So just to put this kind of practically speaking, suppose we have a data set and it has 3 classes. You have trucks, you have cars, and you have cats. The SVM is going to be primarily concerned with that more difficult task of separating the, trucks from the cars, and isn't going to really care how different the car and the cat, scores are, as long as you can generally, kind of get cars correct, whereas Softmax is going to want to push, if you see a car, it's going to want to push that CAT score down to 0. In practice, these yield like very, very similar results, and like some people will argue for one or the other. But if you have a classification task, it's like fine to use either one, and you're probably going to get something very, very similar. Okay, so that's classification loss. And now that we have this architecture in mind, we need to think about how do we actually train the neural networks. And we saw that, very broadly in the introduction to deep learning lecture, but now we'll go into a lot more depth. But before that, does anyone have a question about these losses for classification tasks? Okay, so I'm going to be talking about training neural networks mostly from a more kind of theoretical perspective. And this, there's a lot to cover, so we may end up covering part of this on Wednesday as well, but that's fine because we have, plenty of time still to talk about object detection on Wednesday and Monday's a holiday, Wednesday and next Wednesday. This lecture, we're going to talk about training kind of mostly from a general kind of theoretical perspective. And then after we introduce object detection, next class, we'll return to a discussion of training and practice that's geared in particular towards object detection. And you'll get to see kind of how we actually go in and apply the things that we cover in this class in practice. Okay, so you can see that there are a lot of things on this list. And I think sometimes like it can feel like a bit overwhelming if you just go read the, like the seminal deep learning textbook, for example, and it feels a bit like a laundry list. And it's hard to get away from it feeling completely like a laundry list, but I'm going to try to also like highlight some ways in which these different aspects of training the network interact with each other. And like ultimately, like neural networks is just an optimization problem, but it's a particularly challenging optimization problem that fortunately, like we have a lot of guidance on how to solve. And so I'll start by talking about activation functions, which remember the activation function is how we introduce non-linearity into the network. And if we didn't have any non-linearity, the whole thing would just boil down to a linear classifier, and it would have trouble fitting kind of more complex data. That non-linearity is really important, but we have to introduce that in a very kind of specific and limited way to have any hopes of being able to optimize this super complicated function, that defines your loss function over this neural net that may have hundreds of millions of parameters. I'll say something very briefly about data preprocessing. It's important, but fortunately very simple to implement, especially for images. I'll talk about how you initialize the network, which is important. Like if you start in the wrong place, you're not going to converge to a desirable solution. And as we talked about in the kind of introduction to deep learning lecture, actually one of the reasons why deep learning just didn't seem like that promising when it was first introduced kind of in the 80s and 90s is that they weren't initializing things in the right way, and it really matters. Okay, so once we've kind of pre-processed the data and initialized the network, we need to actually optimize it, and we'll talk about different optimization algorithms. And then we'll talk about regularization, which is how we avoid overfitting. And there's different ways to regularize. We'll talk about batch normalization. That actually has a lot of desirable features, and the primary feature is an even regularization, but we'll talk about how that has a regularizing effect and just also helps us to optimize these really, really complicated functions. We'll talk about dropout and data augmentation, which are methods for regularization to avoid overfitting. We'll talk a bit about transfer learning. And then in practice, how do you choose your hyperparameters? What should you be doing to monitor the learning process? And then finally, we'll talk a little bit about deep document classification and practice. We've already talked a fair bit about ImageNet, but how do we apply this to documents? So this is kind of the roadmap that we'll be discussing today, and probably some on Wednesday as well, since there's a fair amount of ground to cover. Okay. So I'm going to start out with activation functions. And you'll remember in the deep learning video that we saw in the introduction, they motivated it with a function called Sigmoid, which squishes the activations between 0 and 1, but then there was that little note kind of at the end, like, oh yeah, people don't actually use Sigmoid. People use something called Rectified Linear Unit, or ReLU. And this, now we're going to have an intuition for why that's the case. Okay, and so this is what the sigmoid activation function looks like. Basically, at low and high values, it saturates to 0 or 1, and then there's this kind of narrow range in the middle where it increases quite steeply. It's nonlinear everywhere in its domain, and so you would never use Sigmoid. You just don't do that. Like this is what they started with in the 1980s, but like why don't you want to use Sigmoid? And so the biggest problem is that it saturates, kind of across most of its domain. And when it saturates, that means that there's a gradient of 0. Well, what are you doing when you optimize a neural network? You're essentially you're doing back propagation, which is essentially just applying the chain rule like back through this network. And if you have a lot of gradients that are equal to 0, you're going to have a vanishing gradient problem. Your gradients are going to be 0, and you're not going to be able to optimize the network, because with a 0 gradient, then you just get a 0 step and you're not updating. And so the fact that this saturates out makes it very problematic, and it gets more and more problematic as the number of layers in your network increases. But it's problematic even at a couple of layers, and kind of machine learning applications. And when you get into deep learning, it just wouldn't work if you use Sigmoid. It's also going to be very sensitive to changes in a narrow range. And we'll talk about this a little bit more subsequently, but this can be problematic because when you compute a gradient, you're holding everything else constant, right? You're assuming nothing else changes. That's the definition of the gradient. But in practice, you update your network at once. You compute the gradient on the full network, and then you update. If your gradients are going to be super sensitive in this small range, that's going to be problematic. Another problem that you can see is that the output is not 0 centered. It goes from 0 to 1. And we'll talk about subsequently like why output needs to be 0 centered. So I know I'm saying like with a fair number of things, we're going to talk about this in a few slides. And the issue is just like kind of there's a lot to present, and they all kind of interact together. So bear with me. We'll get there. But you need your, like when output is not 0 centered, that can be problematic. And then the final problem is that this is costly to compute. It has an exponential in there. And so it's just going to be very slow, which again is a problem if you're trying to like optimize this network with potentially like hundreds of millions of parameters. Okay, so like Sigmoid was what we had kind of back in the 80s, and you move forward kind of in the 2000s, people started using the inverse or hyperbolic tangent, which is also called tanh for short. And so this looks kind of like Sigmoid, but you see that it varies between -1 and 1. And so it's now 0 centered. It solves that problem. And so that's going to help. Why might we like this? Well, why did people decide to use this? Well, it's nonlinear everywhere, right? Which seems desirable. We have this activation function to introduce nonlinearities into the network. And so that's good. And it's 0 centered. But just like with the sigmoid, it's relatively flat, except for in a very narrow range. And so that's going to be, that's going to, again, lead to major problems with vanishing gradients. It makes the network super difficult to initialize. because there's kind of only this small range that where your gradients won't be zero. And if you're not super careful about initialization, you can kind of just end up with all the gradients being zero and you can't optimize it. And it's not an accident that a key part of AlexNet was to use ReLU instead of TANH. I think that the things that we've seen that are possible with deep learning, it wouldn't have been possible to kind of optimize those kind of functions if you were using a TANH activation. Okay, so that brings us to the rectified linear unit, which is what is used in all the CNN architectures that we saw last class. And so this is very simple. For activations less than 0, it puts them to 0. And for activations greater than 0, it's just the identity function. And so less than 0, it has a slope of 0. Greater than 0, it has a slope of 1. And so why does this work? I mean, you might say, well, like the entire point of having an activation function was to introduce nonlinearity. And this is just like a piecewise linear function. So why is that helping us? Well, we're applying this function over and over again. Remember, we also have the bias term, so we can be shifting this all around, right? And it makes sense, you're applying this piecewise linear function hundreds of millions of times, kind of shifting around kind of where the origin is. And so it makes sense that you're going to be able to fit pretty complex things, even though it is piecewise linear. It doesn't have the severe vanishing gradient problem suffered by sigmoid or TANH, because in this entire, half of it, the positive part of its domain, it doesn't saturate. You do have kind of this entire, negative part of the domain where it does saturate to 0. In practice, if you have a reasonably sized batch, there will usually be some data points giving positive values to any given node. And remember, you're taking the average gradient across your mini batch. And so the average derivative usually isn't close to 0 if you've done a reasonable job at setting your learning rate and initializing the network. And that allows gradient descent to keep progressing. Another kind of good thing about this is that it can actually output true zeros, which is better if you want to estimate a sparse network, and estimating a sparse network could help with overfitting. And then the final advantage, which is pretty huge when it comes to deep nets, is it's just much faster to compute because you just have to compute a max. That's much faster than computing an exponential. So it's about 6 times faster than TANH. And this was, another reason why AlexNet was a feasible thing to do, is because, this function was introduced kind of like a long time ago. We talked about how LENet back in the 90s used it, but in general, kind of people trying to do neural networks, like we're using TANH until AlexNet, which kind of pushed in the direction of using ReLU because it showed great performance and was just so much faster. Okay, there is a problem here, which is called dead ReLUs. So a ReLU neuron is dead if it gets stuck on the negative side, and it just always yields a 0 gradient no matter what the input is. And this usually happens when the learning rate is too large, and we'll get a better intuition for that when we talk about optimizing the network, or when you initialize with a very negative bias. So remember, you're taking the weights, multiplying them by the input and adding a bias. And if that bias is super negative, then the weights just can't overcome that to get the activation above 0. And so you would, in practice, always initialize with positive biases. Okay, you can maybe, solve this with this function that's sometimes used, that's called a leaky ReLU, which avoids, having a 0 slope by having a very slight slope in the negative part of the domain. Or there's something called an exponential linear unit, which in the negative half is exponential, and then linear in the positive range. And so that solves the dead ReLU problem without allowing very negative activations, which you might get with the leaky ReLU if you go far enough into the negative domain. But the disadvantage of this is that exponential is a lot more costly than the max function to compute. And so in practice, you probably wouldn't use this. As I said, like the architectures that we saw last class use a ReLU, but it's good to like know that this exists. And so what's the summary? You probably want to use ReLU. You need to be careful when you set your learning rate and initialize in a reasonable way. Both are things we're going to talk about subsequently in this lecture. And you could experiment with leaky ReLU or the exponential linear unit and just don't use Sigmoid. Like you would not do that. So are there any questions about the activation function and the intuition behind it? Okay, so data preprocessing is very simple. We need input data to be zero-centered and on the same scale. And so, you know, the zero-centered, right, you get kind of an intuition for why you want your inputs to be zero-centered just from the ReLU function that we just saw. And we'll talk about why it needs to be on the same scale when we talk about optimizing. Essentially, if your data aren't on the same scale, it's going to be a lot more difficult to optimize your loss function. So we'll explain that in a minute, but for now, take it as given that we need this to be true. With image data, we don't worry about putting the data on the same scale because already an RGB image or, you know, a grayscale image, a black and white image, they're already on the same scale. You know, if it's an RGB image, there's pixel values from 0 to 255. We do need to zero center the data, and there's two options. So you could just take kind of the mean image in your data, which for ImageNet is going to kind of essentially look like an orange blob. Or you could subtract a per channel mean, which is just 3 numbers. So for the R, the G, and the B dimension, you subtract out the mean R, the mean G, and the mean B value. And in practice, it leads to a very similar result. You know, AlexNet does the first, BGG does the second. You know, in practice, when you go and implement these architectures, it's going to do that for you. And so you don't need to worry about this per se, but it's good to know that this is like happening in the background, but very simple. Okay, which brings us to initialization. So how do we initialize our network? This is actually really tricky. And it's a big part of the reason why deep learning in the early decades had disappointing results. And you know, fortunately, as I said, this is a problem that we know how to address now. But you know, let's think about first why it's actually not a trivial thing to do. So suppose you have a bunch of very, very small weights. Then all your neurons will have close to 0 activations. And again, if we go back and think about how backprop works, that means you're going to have a 0 gradient, as the gradient, you know, at any given layer is the activations times the upstream gradient. And so then that's a problem, because if you have 0 gradients, you can't optimize the network. On the other hand, if weights are too large, you'll saturate the network. And this is particularly true with a function like tanh. And so remember I said like sigmoid and tanh make it particularly difficult to, you know, to initialize the network. And so again, you know, if you've saturated the network, then all the gradients flowing through it are going to be 0. You can train and train and train, but your loss isn't going to move because you're just adding 0, right? And so you need kind of it to be just right in terms of the magnitude. And there was a paper back in 2010, you know, so this is when people were using tanh, called Javier Initialization. And what it does is essentially you draw from a unit Gaussian. So you have mean 0 and standard deviation 1, but instead of just taking those unit Gaussian observations, which tend to be problematic, even with a few layers, your gradients will collapse to 0. Instead, what you do is to just divide by the square root of the number of inputs to each neuron. And so if a neuron is computed by, taking the weighted sum of a lot of activations, a lot of inputs. You'll scale down those inputs by square root of n. If the neuron only has a few inputs, the initial activations will be larger. So this actually doesn't work so well for ReLU, for kind of an obvious and easy to fix problem. And so ReLU, as we saw, essentially kills half the distribution of inputs by setting it to 0. And so there's this paper, he et al. In 2015, and they said, well, you can fix this just by adjusting for this, by drawing weights from a normal distribution that's now centered at 0 and has variance of 2 over n. So compared to the Javier initialization, you're just multiplying the variance term that you're drawing from by 2 to adjust for the fact that now you've killed half the distribution. And so again, I think if you're using like a good kind of model framework, it will probably do the he et al. Initialization by default. But it's good to know that that's happening. It seems like a very kind of simple idea ex post once you see it, but this was not obvious to people for a long time. In practice, you might also initialize with learned weights that you take from a similar application, which is where transfer learning comes in. But we'll talk more about that in a minute. Okay, so are there any questions about how to initialize the network before we move on to optimization? Okay. And so in some sense, as we talked about before, neural nets are actually this kind of very simple and very elegant idea, just essentially using, multivariable calculus and linear algebra to solve all these kind of problems that seemed impossible to solve initially. And so it's pretty amazing. And the most challenging thing about them, and why people thought that this, when the theory of it was proposed a long time ago, one of the reasons they thought it would never work, beyond computing constraints, is just it's this really complicated space. How do you optimize a function that has, potentially over 100 million dimensions? And so we saw when we watched the videos introducing deep learning, how we use stochastic gradient descent for optimization. And so essentially you just take your position and you then you move by a step equal to the negative gradient times the learning rate, where the learning rate is just a parameter that you've set ex ante that tells you how big of a step you want to take scaled by the size of the gradient. And so that's a very kind of simple idea, right? That has this, and we saw how, that took you towards the minimum. In reality, that was to kind of give a general intuition for how we optimize, but you wouldn't actually use just the plain vanilla stochastic gradient descent like we saw in the video. And so it's helpful to think a little bit before we talk about what you would actually do about why it's so difficult to optimize these functions. And so a major challenge is what's called pathological curvature, which refers to regions of the loss function that aren't scaled well. So these are often described as valleys, trenches, or ravines, thinking about kind of what they would look like if you happen to have kind of a network with just two inputs that you could visualize in three-dimensional space. These kind of pathological curvatures might look like a ravine where it's very, very steep in one direction and you're only very, very slightly sloped in the other direction. And in neural networks, these ravines are very common near local minima. And to understand why this is a problem, I think it's useful to note first what happens with a one-dimensional function when the learning rate is too small or large, because we'll see that this is actually kind of quite related to the learning rate. And so here's just a simple figure. And so you see in the first panel, if your learning rate is too low, you're going to get to that minimum. but you're going to move very, very slowly. It's going to take a long time. In practice, that might be, a big problem because you don't have, a month to sit there while your model takes a lot of money to run on AWS, essentially. And on the other hand, if your learning rate is too high, and so that means that the step you take in the direction of that gradient, it's a little hard to see on this figure, but you see that you're taking this very large step. And what happens is you're going to overshoot. If you do this kind of in this overshooting, the minimum, in a best case scenario, you're going to bounce back and forth, back and forth, back and forth. And in a worst case scenario, which you see actually in this picture, you might actually diverge from the minimum. Okay, so we can think about this in now, assuming instead of having just one input in a function, we can visualize in 2 dimensions, assume that we have 2 inputs, and we're visualizing this in 3 dimensions with these contour curves where the lines, the circles represent kind of places with the same output. And so this has been drawn, and so that there's one direction kind of that's very, very steep, and another direction that's sloping very smoothly. And so in the very steep direction, you have a very large gradient. You multiply that by your learning rate, and you're going to overshoot. And that's going to lead you to bounce back and forth, back and forth, back and forth along the walls of these ravines. On the other hand, in the dimension where you have a very flat gradient, you're going to take very small steps. And if you need to get over there kind of to the right to converge to your local min, that's going to be a very small process as you bounce back and forth, back and forth, back and forth. Another related major optimization challenge is saddle points. And so we might think, that the big issue is going to be, local min, because we have this hugely kind of convoluted function. And there's actually work showing that, and it makes sense kind of intuitively. So if you have a function with 100 million inputs, a true local min is going to be really, really rare. That you can't move in any of those 100 million directions and reduce that function. So local min actually are not super common. What is incredibly common is saddle points, where a saddle point just means, it's a local min in some directions and a local max in others. If you have 100 million dimensions, obviously with pretty high probability, it's going to be true that in kind of moving in one direction, you're at a min, and the other direction, you're at a max. And basically at a saddle point, the gradient is very near 0. And so you run this risk of, going down and kind of oscillating between kind of the two, oscillating in one direction and not moving kind of at all in the other, that you need to move in to get out of this saddle point. And so in practice, saddle points are a big challenge, and you're actually more likely to get stuck on a saddle point if you're using just regular stochastic gradient descent than you would to get stuck in a suboptimal local minima. Okay. And another thing that's worth noting is recall that we compute the gradient on the mini batch, where say a mini batch is we sampled 32 images, and those are our inputs, and we're going to compute the gradient over that mini batch because it would be way too computationally intensive to compute it using every image in our training set, which might be like 1 million images. So this is also going to introduce noise. And so the solvers that we're going to discuss are motivated by these different challenges. Okay, and so the first thing I'm going to talk about is momentum. And so you see just the regular stochastic gradient descent first. You update just by moving in the direction of the negative gradient and multiplying by your learning rate, which I've called alpha. Okay, what momentum does is just to make this kind of modest change that actually makes a big difference. So you need to calculate your momentum, which is just a weighted sum of your past gradients, where the weights on that sum are a hyperparameter that we usually set to 0.9 or to 0.99. You probably don't even need to worry about optimizing this. That's just kind of standard. And this is effectively a running sum of your gradients with exponential decay. And so the gradients from a long time ago, you know, if you have 0.9 by kind of 10 steps forward, that's essentially disappeared. And the weight that you put on that is going to decay exponentially. And so why don't we just, you know, remember the past 10 gradients and use those? So the answer to that is memory, right? It's much less costly to keep this running sum in memory than it would to keep these separate gradients and add them up. And so, you know, it's very simple to think about this with just some kind of vector addition. You have a gradient that has a direction, you have a velocity that has a direction, and you just add those two vectors in order to determine your actual step. And so we can think about how this helps us with the valleys or the ravines that we talked about earlier. And so essentially, if your gradients are always pointing in the same direction, right? As you move to the right in this image, you have a very small slope and you're kind of continuously moving little by little in that direction, then your gradients are going to add up and, you know, give you momentum in that direction, right? Which is where kind of the term momentum comes from, something with like a physical application, right? Whereas if your gradients are in opposite directions, which is what happens when you're overshooting and bouncing back and forth, back and forth, back and forth, they're going to cancel and momentum is going to slow you down. And so overall, this is going to speed up convergence because you spend less time oscillating back and forth and you're moving more kind of in the direction with the slow change that you need to move to get to the local min. And this will also help you escape saddle points as long as the momentum is not kind of solely in the dimension of the minima. So this helps kind of, this helps with both of those problems. I mean, you'll see it used a lot in practice. Okay, so you might be concerned at this point that momentum would push you out of a sharp minimum. And that's true, but in general, that's seen as a feature and not a bug. And so the intuition is that if you have this very sharp local min that you can easily get knocked out of, you know, that's kind of very dependent on a very kind of specific part of your training data. And if you have a flat min, that's likely to be more robust to generalization. And so we see this kind of as good as well, that this momentum may actually help you to bounce out of these very sharp local min that may not generalize as well when it gets to test time. Okay. And so there's a slight variation to this that you know, if you're solving one of these models, you'll have the option to turn it on, which is called Nesteroff. And so the basic idea with Nesteroff is that we know that we're going to already move in the momentum direction. And so we might as well just compute the gradient at the end of the direction that we move with momentum. And then we kind of shift it back and use that and move in that direction. So you can see that right here with these figures. So you see that you end up kind of in a slightly different place because the gradient's going to be slightly different at the location you move to with momentum than it's going to be at your initial starting point. And, you know, it might not make a huge difference, but if you add this up over and over again, oftentimes it will lead to, you know, slightly faster convergence. Okay, so that's kind of momentum and a slightly modified version of momentum. So we've seen that momentum solves the challenges of ravines by changing the gradient, by making it smaller in dimensions with oscillation and larger in dimensions with consistent movement in the same direction, much like you get momentum as you're like rolling a ball down a hill. We could achieve something similar by allowing the learning rates to scale differently in these dimensions. And so remember, the learning rate is just a hyperparameter that you choose. It might be equal to like 0.0001. And you can choose to, decay it, or for example, over the course of training, but it applies in all dimensions. Just regardless of the dimension that you're moving in, you have the same learning rate. That's how it's defined. But actually, if we had different learning rates in different dimensions, that would be essentially like equivalent to using momentum to change the gradients, because the step that you move is just the learning rate times the gradient. Or in the case of SGD plus momentum, it's just the learning rate times the momentum term. And so this is also something that's done. It was introduced in something called RMS prop, which interestingly enough, this was not like introduced in a paper, but just like Jeff Hinton, who's one of the kind of leaders of deep learning, he was giving a Coursera lecture, and he was just like, oh yeah, like I found in practice that this works pretty well. Like I've never written a paper, like I can't prove it, but try it out. And then people did, and it worked really well. And so what you do with RSM prop is you just take an exponentially weighted sum of the squared gradients. And so again, what the exponential weighting is going to do is just decay the sum as you move further and further away. And you want to do that, right? Because if you don't decay the sum, then that sum is going to blow up. And so what happens when you so you compute that, and then you just divide the learning rate by the square root of that running sum of the squared gradients. And so what this does is that if you have dimensions that are very, very steep, and so they have large gradients, you're gonna square that, and you're gonna be dividing by a large number, and so you're gonna have a low learning rate. Whereas if you have dimensions that you're trying to move in that are very flat, then you're going to be dividing by a smaller number, and so effectively you're going to have a larger learning rate. And so again, this helps with this, oscillation and slow convergence to the local min and ravines, because you're dampening down your learning rate, so you're going to do less oscillating back and forth, and you're kind of speeding up along the slow direction that you're trying to use to get to the local min. Okay. And so a final optimization algorithm that you'll see a lot is called ADAM, which just stands for Adaptive Moment Estimation. And it combines momentum and RMS prop, right? And the name comes from the fact that momentum is just this running sum of the first moments of the gradient, and RMS prop is just using the running sum of the second moments of the gradient. And so now you're updating by taking the learning rate divided by this running sum of gradients and multiplying by the momentum. In the full implementation of this, there's also a bias correction term that affects the first few iterations. And so you can check that out if you want, but it's not really central to understanding the concept here. So I've stuck with the simpler non-bias corrected equation. And ADAM tends to work pretty well. I mean, people still disagree, and there's papers that disagree about whether this is actually better than SGD with momentum. And so in practice, you'll see them both used kind of interchangeably in the literature. And the final thing that I want to say about optimization is that, if you've taken an optimization class or thought a lot about optimization, you might be asking, well, why don't we use a second order approach like Newton's method? And part of the appeal of that, so first of all, what a second order approach does is just you're approximating the gradient. Instead of approximating it linearly, you're approximating it with a second order function. And so you approximate that second order function, and then you just jump to the minimum of that, and that's your step. In theory, would allow you to converge in relatively few steps. And it has the advantage that you would not have to choose a learning rate, which when we talk about hyperparameter optimization, we'll see that that's kind of the main hyperparameter that you have to worry about optimizing over. Like why don't people ever do this in neural networks in practice? The answer to that, like if you think about it, so in order to determine this step, you're going to have to compute the Hessian matrix, and then you're going to have to invert it. And so the Hessian, which is like your second order, covariance matrix for the gradients, that's like if you have 100 million parameters, that's going to be 100 million by 100 million matrix, and then you have to invert that, and that's just not like feasible like on any computer, right? This is just completely computationally infeasible. And so we kind of have to stick to first order methods for optimization in neural nets because the second order methods are just like totally infeasible. And there's some like approximations to second order methods that let you get around having to invert the Hessian, but in practice they don't really work that well. And so you're like unlikely to use them. Okay, so I know that was, you know, a fair amount of ground. Are there any questions at all about optimization? Okay, so, you know, as I said, in practice, you'll choose a solver, and kind of in the literature, you see most commonly SGD plus momentum, maybe with this Nesteroff correction, or you'll see people using Atom. And it's going to interact with some of the other things you do, like it's going to interact with regularization, and I'll mention that in a minute. But in some, like I said, if you go and you kind of try to look into this, people don't seem to really agree, like which one's better. But just, you know, the bottom line is don't use just the plain stochastic gradient descent. You need some sort of, you know, term that's going to help you in these ravines and that's going to help you get out of these saddle points. Okay. And so the next thing that I want to talk about is regularization. And so we saw, like at the beginning of this lecture, the loss functions that we use for classification. In practice, your loss function includes not just your data loss, and so the difference between your model predictions and your training data that we can compute, like say with like SVM or Softmax, but it also includes a regularization term. And what this regularization term does is to penalize the loss for having a complicated model. And the intuition for you, why you want to do this is just Occam's razor. The idea that the simplest model is likely to be the best model. It's more likely to generalize. And so you want to penalize your model for being too complex. And so in practice, in convolutional neural networks, the most common thing to use for regularization by far is called L2 regularization, which just computes the Euclidean norm, or also known as the L2 norm, which is just the sum over all the squared weights. And then this regularization term is weighted by some scalar mu, and divided by 2 and added to the loss function. The only reason you divide by 2 is when you differentiate the loss function, right? And you take that square term around, the 1/2 is going to cancel, and it will just, you won't have to carry that around. And so that mu hyperparameter that you multiply that sum of squared rates by is known as the regularization rate. And that's something that you would also like optimize over when choosing your hyperparameters. And we'll talk about more how you know if you have enough regularization, too much regularization, too little. And so in practice, what this does is that it favors putting small values on mini weights as opposed to large values on a limited number of weights. In other words, it pushes you to use all your inputs a little bit rather than using some of your inputs a lot. And to see why this is useful, like let's say you have like a training data set that has cats and dogs in it, and you know the dogs are all brown and the cats are all black. And so you know, and say you had, you know, for illustrative purposes, you have a neuron that captures, you know, whether or not the image has a lot of brown or a lot of black. And if you put all your weight on that, so the way you tell if something is a dog or a cat is if it's brown or black, well, like if you get into your test data, the data that you want to apply this model to, and you see some brown cats that you weren't exposed to in training, you're going to perform very poorly, right? Whereas if you have, you spread your weight among a bunch of different features. A cat has ears that look like this and this kind of tail, and it stands this way, and etc. You're going to have a more robust model. So that's kind of the intuition there. Then it also pushes your weight values towards 0, which in itself tends to lead to a simpler model that avoids modeling noise, which is what you don't want to do. You don't want to be just modeling noise in your training data. So something that you'll see in the literature and also in the textbook is that the terms L2 normalization and weight decay are often used interchangeably. Because effectively, if you work out, when you optimize a loss function, what L2 normalization is doing, it's leading you to kind of decay your weights. So this was confusing, at least to me at first, because these are equivalent for stochastic gradient descent as long as you scale by the learning rate appropriately. But this is actually no longer true for the adaptive gradient algorithms, such as ADAM that we just saw. And this point seems to have generated a lot of confusion. I've listed here a paper about this that you can read if it's relevant to you, and they show how you would adjust L2 regularization for ADAM. And they claim that, in neural nets, oftentimes in practice, SGD with momentum does better than ADAM because people weren't adjusting the L2 regularization appropriately, and that ADAM's better if you do that. I don't know that that's like a fully accepted point, but I just kind of note that in case it's of relevance to you. Okay, so does regularization make sense to people? Does anyone have questions? So in practice, there's other forms of regularization. There's something called L1 regularization, where you're just summing up the weights, and that instead will push your weights to 0, like all the way to 0. And that's good if you have a problem where you really want sparsity. That's not kind of generally true in CNNs. So usually in CNNs, we use L2 regularization. Kind of more generally, you can think of regularization as anything that adds some random noise during training. And other methods also have a regularizing effect. So batch normalization, dropout, data augmentation. With something like batch norm, which we're going to talk about now, that's not even its primary intention, but it does have that regularizing effect. And so we're going to talk about these other methods now. And so I want to start by talking about batch normalization, which in practice is really important in CNNs. And so if you recall back, to the beginning of the lecture, we talked about how we normalize our input data, how we want it to be on the same scale and 0-centered, so we don't get these dead ReLUs, so we don't get this pathological curvature. But that's just your input layer. Let's say you have, like ResNet 101, and you have like 101 layers in your neural network. You've only normalized the inputs, not the activations in those 101 layers. And so this insight led to an idea that's very simple, but turned out to be incredibly powerful, which is the idea, if you want your activations to be unit Gaussian, just make them unit Gaussian. And this paper is from 2015, and it's now one of the most cited papers in deep learning. And so in general, what you do with batch norm is just to compute the mean and variance independently across your batch for each dimension and then normalize. And so if you just did that, it would make all your activations exactly unit Gaussian. You might not want them to be just unit Gaussian. You might want them to be able to spread out or shift. And so in practice, you'll also estimate these beta and gamma parameters. These are learned parameters, and they allow you kind of to squash or shift this distribution of activations. And so how does this work in practice? Well, in ComNets, we have these filter rates, right, that are shared across the input image. And hence it's reasonable to normalize the output in the same way. And so what this means in practice is that when you apply these batch norm layers in ComNets, the mean and variance are computed from all the activations in a given features map for all images in the batch, right? So if you have a features map that has dimensions h times w for height and width, and then you have 32 images in your batch, you're going to compute the mean across all the pixels in that layer of dimensions h times w across all 32 images in your batch. And so what this means is that we compute one mean and variance per channel. And so if you have an input that's RGB, that's 3 channels, you're going to be computing 3 means. Let's say that you've just applied 92 of these convolutional filters, and so your output has depth 92. There's 92 different features maps that extract different features from the input using these different 92 filters. Then you're going to compute 92 means and 92 variances and subtract those off of the pixels and the height and width dimensions in that feature map. Okay, so why is this a desirable thing to do, right? It seems like a very simple innovation, and we'll see it made a big difference to being able to actually train deep neural networks, but why is that true? And so the initial paper argues that batch normalization helps to train a network better because of covariance shift. And so we kind of touched on this point at the beginning of the lecture. The gradient tells us how to update each parameter under the assumption that the other layers don't change. But in practice, we update all of the layers of deep neural nets simultaneously. And so if we have ResNet 101, we're updating all 101 layers simultaneously. And the distribution of each layer's inputs change during training as the parameters of the previous layers change. And this necessitates lower learning rates and careful initialization, because in some sense our approximation of the gradient is not as good because of this covariance shift that's happening, because we're not actually just changing one thing at a time, we're updating everything at once. And batch normalization significantly reduces this problem, which helps to both stabilize and to speed up training. However, it's still debated exactly why batch normalization tends to work so well. And so there's another paper, which again, if you're interested in this, I encourage you to go and read it, that argues that batch norm is effective because it smooths the optimization function. And so you can essentially like go back to the visualization we had of what happens in the ravines, where you tend to oscillate back and forth in the steep direction and move very slowly in the shallow direction. And if you've normalized your inputs, and so that you don't get that pathological curvature, and you're doing that at every layer by passing it through a batch norm layer, then you don't get that same kind of pathological curvature. And people have done some visualizations that just show that this batch normalization just makes your entire loss landscape much smoother. There's less kind of saddle points to get stuck in. There's fewer ravines like local mins that take a long time to traverse through. And so some people will argue that actually that smoothness effect is probably why this matters so much. It's not the covariance shift that happens when you update everything at once, but rather just optimization is hard in complicated spaces, and anything you can do that significantly smooths out the space is going to make a big difference. The final thing to note is that batch norm has a regularizing effect because the mean and variance depends stochastically on the mini batch. So you're computing this mean across your height and width dimension for all of the images in your batch, and what images in your batch are stochastic. And so this is the interpretation of regularization, that anything that kind of introduces some noise into your training is a good thing, because then it doesn't let you be reliant on just a limited number of features in your training data. I'll make a note about batch norm and regularization. And so L2 regularization, which we just talked about, no longer has a significant regularization on any layer that is followed by batch normalization. And so if you kind of stop and think about it, well, what L2 regularization is doing is making you decay your weights, and then you're just rescaling everything. So you're kind of undoing that regularization. But of course, you might still want to use L2 regularization. You have some other non-conv layers, it affects your learning rate. If you go and kind of like Google this, people don't necessarily fully agree on whether you should use L2 regularization if you're using batch norm. But in general, it's not such a problem that you're undoing the L2 regularization. That doesn't lead to a deterioration from batch norm, because batch norm in itself is giving you this regularization. So you might be kind of undoing your L2 regularization by renormalizing everything, but that renormalizing itself is introducing some noise that has a regularizing effect. Okay, so just to summarize the advantages of batch normalization, it will improve your gradient flow, because you're taking care of this covariate shift problem. It allows a higher learning rate because you really simplified the loss landscape. It reduces the strong dependencies on initialization, because now you're just renormalizing at every layer. So you have less of these problems of saturation, especially if you were trying to use something like eTanh. It's going to reduce the problem of dead ReLUs because you're renormalizing in every layer, and it's going to act as a form of regularization, which is also going to be helpful since it may undo other forms of regularization. So ResNet applies batch norm after each convolutional layer, and some people say that this is as important as the residual connections, in order to explain why they're able to get such an incredibly deep network. Remember, you jump from VGG with like 15 and GoogleNet with 22 dimensions to ResNet 156 or 152. It also helped to improve the accuracy and speed of the GoogleNet inception model. The first author on the batch norm paper is the same as the first author on GoogleNet, I think. So probably it was developed in part to try to make GoogleNet work better. Okay, are there any questions at all about batch normalization? Okay, so in the final few minutes, I'm going to talk about dropout, and then we'll cover the rest of these topics on Wednesday, and also move on to start talking about object detection on Wednesday. Okay, and so the idea behind dropout is that at each stage of the training, each node is randomly kept with a given probability. So you do this in practice by generating a binary mask that consists of zeros and ones, and 50% zeros, 50% ones if you chose 0.5. Then you just multiply the activations by this mask, and it has the effect of removing those activations. And then you also do this on backprop, right? So those gradients are going to be 0. And so you might think, well, like, why would this be a good idea to just kind of throw out half of your neurons? Well, the reason is that it's a form of regularization. Again, it's going to force your network to not be too reliant on any given neuron or feature. Instead, your network's going to have to spread out its ability to do whatever you want it to do across multiple neurons. And this makes it less likely to overfit idiosyncrasies in your training data. Importantly, you would use dropout on fully connected layers. It's less helpful on the conv layers. And so why is that the case? Well, if we think about what conv layers are doing, they have this spatial relationship encoded into their features maps, which is like the entire point of a conv layer, to have this this spatial relationship. And that makes the activations correlated by construction. And so when you drop out, it's not going to do as much because your activations are correlated to start with. Also, you recall that part of the point of COMNETs is to dramatically reduce the number of parameters relative to fully connected layers. And you have fewer parameters, so you don't need as much regularization on comp layers as you would need on fully connected layers. Also, it's probably not a good idea to use bash norm, which is really helpful on the comp layers with dropout, because you know, now dropping things out is going to make your normalization noisier. And so what the literature recommends is you use bash norm on your comp layers, and you may want to use dropout still on your fully connected layers, you know, potentially in addition to bash norm. And so, for example, remember we saw that VGG architecture last class had those fully connected layers at the end that were like over 100 million parameters. Most of the parameters in VGG came from those fully connected layers at the end and not from the comp layers. They use dropout there because, you know, with 100+ million parameters, you're at a lot of risk of overfitting, but didn't use dropout on the comp layers. ResNet used bash norm in its comp layers. And if you recall, in GoogleNet and ResNet, which are in ResNet, the state of the art, we moved away from those fully connected layers towards using comp layers. And so in practice, dropout may be kind of less relevant for image tasks because we've kind of moved to using architectures that don't have fully connected layers, but it's worth knowing that it exists. And the final quick note about dropout is you want to test and do model inference using the full network, right? Obviously, when it comes to test how well you're doing and then to apply this to other data that you didn't see at training, you don't want to handicap yourself by using only part of the network. You want to use the full network. And you need to do this, you need to either scale down at test time, which means you just multiply all the activations by 1/2 if you dropped half of the neurons, or scale up during training. So if you drop half of the neurons, you multiply their activations at 2. And that way the scale is the same at test and train. And this has kind of the interesting implication that we can think about batch norm as essentially like our final model is almost like an ensemble of all these different models that we ran with slightly different randomly dropped neurons, but they have correlated inputs, right? Because we're only dropping 1/2 each time, and they're each only trained on one image, but we can almost think about the end result as being this ensemble that combines information from all of these slightly different correlated networks in order to reduce overfitting. Okay, so that's all for today. Feel free to stick around if you have any questions, and we'll pick up on Wednesday. We're almost done with this, but we have a few more topics to cover. So thank you.